Type CFM calculator into a search box and you will get one formula. Use it for every room or process, and the answer can be confidently wrong. The correct calculator begins with a mode switch, room air changes, people and area ventilation, or source capture. Let's run all three, then turn the result into a fan duty point. First, the room air change method. Measure the inside length, width, and average clear height. Our example studio is 20 feet long, 15 feet wide, and 10 feet high. Multiply them, the room volume is 3,000 cubic feet. Now choose the required air changes per hour, or ACH. That number is an input from the applicable code, owner requirement, process standard, or risk assessment, not a universal value copied from an online list. For an illustrative 6 ACH, multiply 3,000 cubic feet by 6, then divide by 60 minutes. The result is 300 CFM. The formula is simple: CFM equals room volume in cubic feet, times ACH, divided by 60. It tells you the airflow that replaces an equivalent room volume 6 times per hour, assuming the air mix is well enough for that model to be useful. In metric units, the same logic is even cleaner. Cubic meters per hour equals room volume in cubic meters times ACH. To convert cubic meters per hour to CFM, divide by about 1.699. Keep the units visible in every input box. Feet entered into a meter field can create a result that looks precise but is completely false. Second, occupied rooms may use a people and area method rather than a single ACH. A common ventilation rate structure starts with a breathing zone quantity, the people rate times the number of people, plus the area rate times floor area. The rates depend on occupancy category and the adopted standard. Do not invent them. Additional corrections may be required for air distribution effectiveness, system type, outdoor air fraction, or local exhaust. The calculator should therefore ask for the source and addition of each rate. Third, a process is not automatically a room ventilation problem. Welding fumes, vapor, dust, heat, or odor may need local exhaust that captures the source before it spreads. The first geometry relationship is airflow equals capture velocity times effective opening area. But the required capture velocity and hood geometry are process specific. Crossdrafts, enclosure, worker position, duct entry loss, air cleaning, discharge location, and hazardous material rules all matter. For a hazardous process, use qualified industrial ventilation guidance. Do not solve it by choosing a high ACH at random. Now place the three modes on one decision board. The room method gives an air change requirement. The people and area method gives an outdoor air starting quantity. The process method gives source capture or dilution exhaust. Apply the methods that actually govern your application, keep their boundaries separate, and select the required operating scenarios. Do not blindly add supply and exhaust values as if both were independent clean air deliveries. Also provide makeup air for exhaust so doors, combustion equipment, pressure relationships, and hood capture behave as intended. Next, include time. A meeting room may have a design occupancy that occurs for 1 hour. A process hood may run only when a machine opens. A greenhouse or livestock building may need staged seasonal ventilation. Define normal, peak, and emergency modes. The fan system and controls must cover the governing simultaneous condition, not an impossible sum of every nameplate maximum. Here is the critical handoff: calculated CFM is not yet a fan selection. Add filter, coil, duct, elbow, grill, damper, hood, and discharge losses at that airflow. The pair airflow plus static or total pressure is the duty point. Then check that point on the exact fan curve, with voltage, speed, air density, sound, and installation configuration stated. This real Longwell inline mixed flow family shows why the handoff matters. A compact duct fan may be appropriate for a short ventilation run, but the delivered airflow depends on system resistance. Compare the required point with the exact model curve. Never choose from free air CFM or duct diameter alone. Finally, commission the result. Measure airflow with a suitable method, verify pressure relationships and direction, check noise and vibration, and record the control setting. If the measured result differs, inspect blocked grills, dirty filters, closed dampers, duct leakage, poor inlet conditions, and missing makeup air before simply increasing fan speed. Your calculator output should fit on one card: method, source of the rate, dimensions and units, occupancy or process inputs, normal and peak airflow, makeup air assumption, required pressure, and verification plan. Send that card to Longwell with voltage, noise target, installation space, environment, and quantity, and we can turn the airflow calculation into a defensible fan candidate.